remember in the beginning of the chapter, we learned about this, we learned this formula, y equals ab to the x. So what is that? This is the general form of an exponential function, all right? That's how all exponential functions look. Now, that mathematical function has been modified to a formula that could model exponential growth, right? So what are some things that are that change according to exponential growth? We talked about population. We talked about population of people, animals, bacteria. Radioactive decay, right? Like if you have an isotope of uranium, it decays, right? It goes through radioactive decay. That is exponential growth. So the way in which this is different from our other formula where we had y equals a 1 plus r to the power of t is this. 1 plus r to the power of t, this is used when a population or when something changes by a fixed amount every single year, 12% every year. So for example, your car, the car loses value at, like, let's say 12% every single year, right? For that, this a 1 plus r to the t is a good formula to use, okay? But what if you do have radioactive decay? What if you're talking about like this sample, okay? And let's say the half-life of this is 10 years. So when 10 years go by, how much of this substance will remain? Half of it. When another 10 years go by, how much will have remained? Half of that. So this is gone, this is gone. When another 10 years go by, this much will disappear. In another 10 years, this much will disappear. So do you see how you can't say that like 15% is disappearing every single year? Because this is happening continuously. This is something that's a continuous growth or a continuous decay. For those, we have this formula. It's modeled directly after y equals ab to the x. You realize this is also the same thing, right? A something to the power of x. And so is this. This is by far the most popular formula for exponential functions. And it's f of x equals a e to the kt. Other ways that we see it are n is equal to n naught e to the kt. Okay? When we're talking about exponential growth. When we're talking about exponential decay, then we have this version of it, a e to the negative kt. Now, what does a represent? The initial amount, and t is time. K is a constant, and it's particular to, it's unique to each problem, and this is the rate at which something is changing. Now, I do not, under any circumstances, want you to memorize two formulas. Okay? It's just this, a e to the kt, and if it's exponential growth, k is just a positive number. If it's exponential decay, k is just a negative number. That's how we do it. That's how grown-ups do it. That's how we're going to do it. Okay? There's no reason to overcomplicate things with two different formulas. It's the same thing. Okay? Yeah. Huh? Right. Yes. Okay. So look, yesterday we learned about this formula. A equals P e to the RT. It's the same exact thing. Look at it. F of x equals A e to the kt. It's the same exact thing, right? And we use this because we said, okay, what if the bank is paying you interest continuously? Right? So it's the same thing. Continuous rate of interest, continuous growth, da 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 da. Okay. Now, let's, yeah, really, if I wrote my Algebra 2 book, all this would be different, okay? So it's all about this. Really, it's all about this, okay? N equals N naught e to the kt. I like this because it uses the same variable. There is no y and a. It uses the same variable. This just means initial, and this just means final. And then everything else is based on this. Now, the a equals pe to the rt. Okay, I can see the use for that because just for the world of finance, right, where you've got like principal and rate, you might as well just modify it to fit your language, right? Okay, so let's talk about carbon dating. Carbon dating is the process where you look at the amount of carbon-14 in a fossil, let's say, and we know that carbon-14 has a specific half-life. So, you know, based on like the size of the bone, we know how much carbon should have been there at the start, and we can measure how much carbon there is now, and we can figure out how many years this has been buried. Okay, so carbon dating is looking at the half-life of carbon-14 to date organic or living materials. So it turns out carbon-14 has a half-life of 5,730 years, and we want to determine the value of K. And we're given no information, no initial amount, no final amount, nothing, and we're going to be able to find K. All right, so let's get started. Let's start with this formula. Y equals A e to the KT. Okay? Y is the final, A is the initial. Okay, so this 5,730 years, is this Y, A, K, or T? It's T because this is the number of years. That's the time. Now, every time 5,730 years pass, how much of the carbon is left? Half of the initial amount. So if I started with Y amount, and now 5,730 years pass, how much of the Y is left? Half of the Y is left. E to the KT. Okay, and now, since this is decaying, it's negative, and also for the T, I'm going to put in my time, 5,730 years. Okay? So now, oh my gosh, wait a minute. Hang on. Rewind. Sorry, let's rewind. Okay, what did I do wrong here? Yeah, so the initial amount was A. I'm sorry. The initial amount was A. And the final amount is half A. Okay? Now, what can I do to the A's? You can divide both sides by A and the A's just go away. So now I have 1/2 is equal to e to the negative 5,730k, right? So now, can I write this as an ln? Right? ln, so that's log base e, ln of what? 1/2 is equal to the exponent. And now how am I going to solve for k? Divide. So k is what? It's ln of half over negative 5,730. And what does that give you? What value? It's a very small number. Okay, so it's ln of 0.5 divided by negative 5,730. So it's this. So there are 4 zeros. There are 3 zeros. 0.00012. Okay? How do you know this? Okay, because it's scientific notation. So this is 1.209 times 10 to the negative 4. Times 10 to the negative 4 means here between the decimal, so it's 1.2, right? You have to move the decimal point 4 times to the left. 1, 2, 3, 4. No, because we're then gonna put it inside the thing. Let's go with this one. So this is how much K is. This is K, 0.0012. Okay? Huh? Yes. So now, if we were to write the equation for this, for carbon-14, it would be Y equals A E to the negative, this was negative, right? Negative 0.0012 T. Okay? Now this is just asking you for K, so it's good enough to leave it as K. Okay? All right, so here's another one. The half-life of sodium-22 is 2.6 years. Determine the K value and the equation of decay. So I'm going to let you guys do this one. I'll give you 2 minutes. You're going to find K, and then you're going to put it in the equation like I did here. All right? So 2 minutes. I'll stop this for 2 minutes and come back. So we do get negative 0.266 for K. So the equation is AE to the KT. Okay. Now, part B says a geologist is examining a meteorite, and he estimates that it contains about 10% as much sodium-22 as it would have when it reached the Earth's surface. How long ago did the meteorite reach Earth? So now we're looking for T, right? So it's Y equals AE to the KT, right? Now, currently, it's got 10% as much as it had initially. So it's 1/10 of what? A. So it's 1/10 of A equal to A e to the negative 0.2666 T. The A's will go away. So ln of 1 over 10 is negative 0. All this times T. So T is ln of 1 over 10 over negative 0.2666. And we're going to approximate that to be how many years? So it's about 8.6, and we can round it to 9 years. All right, questions? So here's the next one. In 2007, the population of China was 1.32 billion. In 2000, it was 1.26 billion. Determine the value of A for China's population growth, right? So Y equals AE to the KT. How much is Y? 1.32. And A? 1.26. E to the K times what? 7. Awesome. So, well, it's growing. So we divide by 1.26, and that's equal to E to the 7K. So ln of all of this is equal to 7K. So how much is K? Negative 0.0.
No, 0.6512.
Are you sure? It must be a much smaller. That's what it is. 0.0066. Go to 4 decimal places.
Yeah, it shouldn't be negative.
Oh, I'm sorry. It's not negative. I'm so sorry. Yeah, it's K is 0.0066. All right. So here's just K. When will China's population reach 1.5 billion? So now I need my equation. Y equals AE to the 0.0066 T. Now, when will the population reach 1.5 billion? So now y is equal to 1.5 and t is what I need to find, right? So, and actually, you know what? Can we stop for 1 second? The model, when I ask you for the model, which I will, it's going to be y equals the initial amount, which was 1.26 times this. So this would be the model for this problem. For this particular China problem. Okay? So you put the A in there as well. So y equals then 1.26 e to the 0.0066 t. I'm sorry, y is what? 1.5. Okay? So we solve this. I'm going to let you guys do the solving. So how much is t? So it's 27.24 years. Now, it doesn't say in how many years. It says when. So let me just put it in the calculator. All right, let me put it in the calculator. So it's ln of 1.5 over 1.26. Okay, let's see. Divided by 0.0066. So it's 26.4. Okay, so look, so this is, it really doesn't matter because this started in 2000 in 2026. So it doesn't, so whether you wouldn't go, right? So you wouldn't go 27 years. Yeah. Yeah, so in 2026. Okay? Now, India's population in 2007 was 1.13 billion. And its growth is modeled by this. Determine when India's population will surpass that of China. So this is the one for India, right? So 1.13 e to the 0.015 t. And what was the expression for China? 1.26 e to the 0.0066 t. We want India's population to surpass, so to go greater than China's. So in here, I'm not going to put an equal sign. I'm going to put a greater than sign. Okay? So let's go ahead and solve this now. So we divide 1.13 over 1.26. So let me pause this for a minute. So exactly what we did here, where we were taking the logarithm of both sides. This was in section 7.6. We're going to do the same thing here now, but with ln. So what I want to do is I want to take the ln of all of this and the ln of all of that. When I do that, so I have ln of something times something, I need to expand. So it'll be ln of 1.13 plus ln of e to the 0.015 t. Okay? And greater than ln of 1.26 plus ln of e to the kt, 66t here. Okay? Now, yes, the ln and e's will go away. So I have ln of 1.13 plus 0.015t greater than ln of 1.26 plus 0.0066t. Now, move all the t's to one side. and everything else to the other side. So I'm going to subtract 0.0066t from both sides. So it'll be 0.015 minus 0.0066. That'll give me 0.0084t. Greater than ln of 1.26 minus ln of 1.13. You're condensing it. It'll be ln of 1.26 over ln of 1.13. Yeah. So now this is going to be 0.0084t is greater than, so let's condense this, ln of 1.26 over 1.13. And now let's see, this is when t is greater than, so ln of 1.26 over 1.13 divided by 0.0084. Yeah, it's about 13 years. Okay?
So, that's 13 years from what? 13 years from 2007?
Uh-huh. Yeah, 13 years from 2007. Yeah. Okay, so look. So this is in 2007. In 2007, China's population was 1.32 billion. Oh, wait a minute. I'm not. Right? China's population was 1.32 billion in 2007. It wasn't 1.26. So all of these 26s should be 32s. This is the benefit. This is the benefit of leaving the calculation to the very end. Because, here we go, then you just change this and it's easier. Okay? So now it's going to be 18 years, right? So it would be in 2025. Okay? Yeah. All right? So that's what it is. Okay, so now you can start on your homework.